Okay, we'll continue with the next section, which is parallel and multithreading functions. And here we will cover the basic concepts in parallel programming. Also, we will get the knowledge on the tools for parallel programming in different languages. And today, we will talk about Matlab. And also, we will get familiar with the tools to monitor their usage of resources. So here is a definition of parallel programming is the art of writing a code that execute tasks on different computing units. They are called cores. And the key point here is that the tasks are executed simultaneously. So in the past, the computers had a single core per central processing unit CPU, and therefore they could do only a single computation at the time. So, but now normal machine or standard machines, PCs or laptop, they contain several cores in the hardware. So you can check this, for instance, if you go to tools in Windows, like a task manager, right? Which is also, there is also a version in Mac that is called Activity Monitor, as far as I remember, where you can take a look at the number of cores that you have and also memory, right? And here you can see that now, currently, the architecture is more complex than a single core. For instance, this is my local machine that runs Windows, and it contains six cores, right? So now architectures are complex, right? They are hybrids, and they contain different types of architectures. And here I mentioned the two architectures that are the basic units. The first one is called shared memory, where we have some cores. In this case, I only depicted two, but current machines can have up to 120 cores per node that can share some memory. And the advantage of having this architecture is that the bandwidth to transfer data, yes, from the cores to the shared memory is quite fast, right? So if you want to achieve something that is fast, you will target, or you should target, this shared memory architecture. But the problem is that this type of the programs that run on these architectures only scale up to the number of cores that share some local memory. So if you want to scale your program even further, and you require a lot of computations, right? So then in that case, it's better to use distributed memory, where the cores don't share directly the memory, as you can see here, but they can get information from the others by exchanging messages, and the message passing interface API is a standard way to perform this data transfer. So this is how it looks, a standard node on Kebnekaise. And you can see here that this follows a shared memory architecture, right? For some of the cores, in this case, 14 cores that share some global memory, but they are connected through another, the so-called socket, right? And because of that, in total, it looks like they are having twice this shared memory, right? So the GPUs were mentioned previously by Birgitte, and they are kind of a shared memory architecture, but they are also more complex. I won't cover that in the present lecture. So why is parallel programming needed? You have seen that even in a standard machine, as in my local machine here that are running Windows, there are several cores, but if you run your MATLAB script, right, without any type of parallelization, it will run on a single core and you won't take advantage of all the cores and memories that are available. That's why you need to make your code aware of these capabilities. And before I mention some of the tools that MATLAB offers to parallelize your code and to get a better performance. Also imagine that the machine that we are talking about, Kebnekaise, Cosmos, and Raqqa, they have a more complex architecture because here we have many computing nodes, right, that you could exploit in your coding, yeah? And we also need a way to send the jobs from the login nodes to the compute nodes. And that's why we talk about the sbatch and batch command or parpool, right? So that the jobs here are sent to the compute to the computing nodes and they are not executed on the login nodes. So it's important in HPC and especially in HPC, right, where you can allocate many cores that you make use of them in an optimal form. And in order to do that, there are several tools that you could use at our centers, right, to monitor the resources that you allocate. In particular, for instance, at HPC2N, we have a tool that is called the job usage, right? So you click on this link here, you will be sent to this part, to this plot here. And here I explain you how to use this tool. So once you submit the job to the queue, you can get the job ID, which is a number that is listed in the job ID column, and then use this command on the terminal, job usage and the number, and then you will get a URL that you can copy and paste in your local browser, and this will display the CPU utilization, the memory consumption, and also if you allocated the GPUs, then you could see here the statistics as well. So this is important because in HPC you can request many cores, but if you forget some library or you forgot some command, imagine that instead of writing par4, you wrote only 4, and this will run on a single core, even if you request 100, right? So you will be wasting your project time in that way. So it's important to monitor, and at other centers, UPPMAX and Cosmos, there are other tools. At UPPMAX, there is a command called top, which is especially convenient because here you can have an interactive session on the computing nodes and you can monitor on-site the resources usage. So there are several types of programming paradigm to take advantage of the shared memory architectures and the distributed architectures that were mentioned at the beginning. And MATLAB has several tools to do this, right? So there are tools for doing this already. MATLAB is a rich language, right? And I will start with the first paradigm called threaded programming. And the key point of threaded programming is that it takes advantage of the shared memory of the course, which I mentioned before. It has a high bandwidth in the order of terabytes per second. So if you go to some low-level programming language like Fortran, so there are some APIs, application programming interfaces, that allows you to do this threading programming. One of them is OpenMP, and several libraries, especially linear algebra, use OpenMP behind the scenes. And here you don't need to change your code, right? Only you just need to set some environment variable for OpenMP, as it is mentioned here, OMP num threads, and this will make your code parallel, right? So in the case of higher level languages, as in Matlab, they can make use of these external libraries, right? So you can tweak them by using some environment variable. So I wrote here a warning, right? Because now we are talking about threaded programs, and this can immediately lead you to some over over usage of the resources, right? So and that's why it's convenient to monitor the use of the resources as your simulation starts. So in the case of MATLAB, and this is something that I have seen several times, I would say, at this point. And this is only one way that you can do, or that your code can lead to some over exceeded resources. For instance, if you use a simplex solver or you use another solver, right, inside a par for loop. So simplex already have some threaded mechanism. This is something like I mentioned before. It's like an external library that contains already some threaded mechanism that you can activate, yes, by setting an external variable. And in this case, it's called simplex param threads. So if you don't pay attention to this type of variables that set the number of threads of your external library, then this could lead to some overusage of their hardware. Why is that? Because if you include a function that calls a simplex solver inside the par for loops, yes, and the number of threads is greater than one, yes, and you only requested n cores, for instance, then you immediately over exceed the resources. And if you monitor the resources with this tool that I mentioned here, in our case at HPC1, you will immediately see that you are over exceeding the CPU that is allocated. So this causes problems, and when we detect it, we contact the users, and it causes issues with the computing nodes. Here I wrote some language-specific nuances for threading programming in the case of MATLAB, and this is very new. Starting from the version 2020A, MATLAB offers some internal threaded mechanism called the thread pool, which can leverage the power of the shared memory for the threads. Yeah. So this is good, and your code, if you use this pool here, then your code will be faster than if you use the distributed cluster, for instance. But of course, your code will scale only up to the number of cores that are available on a single node. So this is a new feature of Matlab. Is promising. So in the second model for parallel programming, we have the distributed programming, and this will allow you to scale your code for more than hundreds of cores, right? And over several nodes. So in this case, the processes, we are now talking about processes in the nomenclature of the distributed programming, or even they can be called workers, depending on the language, for instance. And they don't share the same memory space. They have their own memory space. And if they want to get data from the other processes, they need to send and receive messages, and they use APIs to do this. And in particular, the message passing interface is a standard MPI for doing this message exchange. So here I wrote uh, some lines for Matlab specifically. So here in Matlab, we can use the par pool that I mentioned. And here you write the name of your cluster, and X is the number of workers. So notice that this is important. The total number of processes that are spawned will always be X plus 1, where the extra process handles the overhead of the rest. So this is not that important if the central process is not doing intensive computations. But if you are occupying all the processes to do the extensive computation, this could lead to some overhead as well. So notice that up to uh, my current knowledge, so MATLAB doesn't support direct MPI calls, right? So, but this is more advanced and also more specific. So if you want to run MPI in MATLAB, you can do it through the MX functions. Here I wrote some lines for the big data in case you have a large data array. And in MATLAB, there are several tools to deal with this kind of arrays. In particular, these are two good options to do that are called tall arrays and also distributed arrays that will allow you even to partition the computation over different workers if you want to process large arrays. Yeah? So let me see how I am with my time. Okay, now we have a break. Okay, we'll talk about the demo for MATLAB parallel programming with a simple example. And here you can see a for loop that is language agnostic. So it's a for loop that starts at 1 and ends at 4. And here I am executing a specific function. In this case, it's just waiting 1 second, yeah? And then we finalize the loop. So this wait 1 second only mimics a more complex function that you would be or you could be executing in your research workflow. For instance, if you have here something heavier, right, that you want to execute in parallel mode. So this is how the function will run by using a single CPU or single core. Here you run the 1 second, then wait 1 second, and so on. So because there are 4 iterations, your code will take about 4 seconds. But the idea is that, and because there is no data dependencies in this part, right? It's just waiting 1 second. So the data at each iteration are independent from the previous and the other iterations. So I can separate the executions in different pieces, right? So in this case, I separate this loop into 4 cores or 4 CPUs. And these functions are split and they are sent to the different CPUs. And because of that, instead of the 4 seconds, this code will take about 1 second duration. Yeah? So here is an implementation in MATLAB. And to mimic this waiting of 1 second, the MATLAB can make use of this pause function to wait for some number of seconds. Here we need to add the MATLAB module that we want. In this case is MATLAB 2023 version. I will add it. As you see here, ML stands for module load, and this is the MATLAB version that I have. So this should be available already. And I can call this script sleep or sleep.ml, for instance. So here I can copy the content of this script, yeah? And then I can start my MATLAB session. Let me see if I don't have this script already. No. So I will start my MATLAB session here. And remember to start it with the dash single conf threads, as I am doing it here. So then I can create a new script, yes, and I will paste my function that I copied with this button here. It's quite convenient. Then I will save this as a script that is called sleep.m. Yeah? So now it is saved in the current directory. So now we will explain you what it does. First of all, I create a function, and this is a function in serial mode. That's why I call it serial. So it takes as an input the number of iterations. Then it gives us an output the serial time. So I am doing the timing with the tick and tock functions in MATLAB. So here I return the tock, which is the difference. Yeah? And here this is a for loop implementation of the instruction that I mentioned before. It's a loop from 1 to n, and then it will pause for 1 second. Yeah? So then if I want to parallelize this function, in MATLAB, there is a command that I mentioned in the first part of this lecture that is called par4. So basically, you only need to substitute the 4 with the par4 with the constraints that I mentioned for par4 for the data. Yes, that is inside the par4 loop. And then I take the time with the tick and talk and return the parallel time. This parallel function also accepts a input argument n. Yeah. So now I have the two functions here in the same script that I call here sleep.m. And there are several ways to execute these functions that we mentioned previously. One is by running the function with the batch job from Matlab. Yeah. The other one is by creating a bash script and then submit the job with the sbash slurm command. And here I mentioned the more interactive way, that is by using the sorry, I will mention here the batch command. Yeah. So I thought I will show you the part. Well, no, I will show you the batch implementation from Matlab. So how can we do this? First, we get a handler for the cluster. Yes, in this case, because we are on Kebnekaise, this is called Kebnekaise, and there should be a counterpart in Cosmos and also at Rackham. Here we set the number of iterations to 4, right? And here we launch the function first, the serial function, which accepts, which has one output, yes, just the serial time. And this is the list of the arguments that is only the number of iteration, which is 4, sorry. And this is a string that should be there, is pool. You shouldn't change this. And finally, the number of workers. And because this is a serial function, we only need one worker. So we will wait for the job, yes, to be executed. And then finally, we fetch the outputs that will be printed out in this t by using this t variable here. After that, we can launch the parallel function, which accepts similar arguments. But notice here that we will use 4 workers. Yeah, 4 workers that will solve the four iterations in the for loop. Yeah, then we will wait and then we will fetch the results. So because we are submitting this to the queue with the batch function, then these functions won't be executed on the login node. They will be executed on the compute node. So I can run this with this button. But if we want to execute this function without the batch job, then we will be running the job on the login node, and that shouldn't be done. You mustn't do this. But in this case, we are in the safe mode. We can run this. We click on this one, and you see that this is submitting the job. So you can see here that the job is allocating some number of CPUs and also the name of your project and the time and so on, yeah, depending on how you configure your cluster. So then because we use the option wait, so you won't be able to use the MATLAB command window until this job finishes. it will fetch the output, and you can see here that it printed out the serial time, which is about 4 seconds, and then it printed out the time for the parallel version, which is about 1/4. Yeah? So notice that the create this is more specific. Yeah, it's by creating more workers, you pay some extra overhead in your calculations. That's why this is not perfectly one. Yeah, but this overhead can be okay. So if your function that you want to execute here in the loop is heavy enough, and you don't care about extra seconds. Right? But in this case, it's important because I had used one second. So, okay, this was for the demo. If you have any questions about this point. So then we have the two exercises. In the first one, you will monitor the performance of a MATLAB function, which does a 2D integration. Yeah, and here you use the par4 to parallelize the loop. And here we use a different way to run the MATLAB, which is more interactive. And this was also mentioned by Birgitte. Here you will use the parpool. Instead of using this command batch and get a handler, then you just open a pool of some number of workers, and then inside everything that you execute, and it contains the par4, spmd, parfeval, parsim, will be executed on the computing nodes. But again, notice that if you have some a serial function, like in this case, the sleep serial, and you execute this inside the parpool, this will be executed still on the login node. So pay attention to this and don't run anything heavy on the login node. Only these instructions will be sent to the parpool. So here you will monitor the performance. You don't need to do the coding of this function. It's already there. And you can run the script with different number of cores, right? To see how are the timings and what is the optimal number of cores for this simulation. Then you can also monitor the usage of the resources by running the job usage command at the SPC2N or top by UPPMAX or LUNARC, for instance. And then you can see how the resources are used. And this is especially important in parallel programs because, for instance, imagine that you allocate here some number of workers, let's say 4, but here you only have 2 iterations. Yeah? So you will be allocating more resources than what you need. On the contrary, if you allocate less workers than you really need, then that could also be reflected in the performance that you code, and eventually you can overuse the allocated resources. It's important to pay attention to this, and this exercise will help you to this, hopefully. In the second one, I think it's more realistic from my point of view. You would decide about this. It's more advanced as well, because here you need to do some coding. This is for a data frame where you can partition the data frame into pieces for the single workers, and then you can do some computation over the pieces of work. In particular, you will compute the mean for each piece, and then you collect the total mean. It's equivalent to perform the average, for instance, over a large column of data. Yeah. So this is more realistic, and here there are some solutions. So let me know how it goes, and if you have any comments about this material or any questions, just let me know.